What's up, chem nerds? This is the Kinetics and Equilibrium review video. Right beside me I have honey green tea with boba, and now I'm ready to start this video. Here are the list of topics that we're going to go over: reaction rates, potential energy diagrams, factors of reaction rates, collision theory, equilibrium, and entropy. And let's start with reaction rates. Okay, right here, the rate of reaction is the speed at which a chemical or physical change occurs. And if you look at our diagram to the right, we have an example of the two different substances, X and Y. So let me label them. So we have two substances, X and Y, immersed in water. And after 5 minutes passes, this is what happens. Now tell me, which of these have the faster reaction rate? And how would you know? It will be this one right here. And how would you know? Look right here. There's less of this remaining than over here for X. So that means more of substance Y has dissolved within 5 minutes, therefore the higher reaction rate. And when you look at chemical reactions, for example, let me write one here. A plus B yields C and D. Forward reactions go to the right. So this is the forward. And reverse reactions go to the left. So that's for a reference for later. Because you're going to see a lot of questions that may say forward reaction or reverse reaction, and it's important to know which way you're going when reading an equation or potential energy diagrams later. Now there's this thing called activation energy, and it's the energy needed to start a chemical reaction. So you need energy to activate the reaction. Just look at the name. Now, so what's important to know is that having low activation energy leads to this, faster reactions. So ideally, if you want to speed up the reaction, you need to have low activation energy, a little amount of energy to start it. Whereas if you had high activation energy, you need a lot to get it started. And that's where we get catalysts. They serve to lower that activation energy, lower it, and speed up reaction rates. So that's important to know about catalysts. There are these substances that you could add to reactions just to lower the activation energy and speed things up. They catalyze the reaction, essentially. And so this leads into what we call the heat of reaction, delta H. And this is the overall energy absorbed or released during a reaction, and we can determine this by this value, this equation, sorry. Delta H is equal to energy of the products minus energy of reactants, so products minus reactants. And so what happens if you get a positive value? This we call endothermic. So you absorbed energy, and the products have more energy than the reactants. In terms of energy, products is greater than reactants. Now what happens if you have a negative value? That's what we call exothermic. That means you released energy, and the reactants have greater energy than the products. So you end up with less after the reaction. Now if you remember on the reference table, there's this thing called table I. In case you don't remember the difference between exo and endothermic, positive or negative, then you're going to have to look at table I because it's listed there. So table I gives delta H values for a variety of reactions. Okay, so here is the potential energy diagram for an exothermic reaction. Woohoo! Okay, so this shows that you start here on the left side with your reactants. You go up, gain some energy, what we call the activation energy, which is right up here. We reach this summit called the activated complex. So at this point, that's when the reaction starts, and here we go. We release all the way down here. We end up on the product side. And because it's exothermic, we release all this energy, and we end up with less than what we started. So right here, our delta H is our difference between products and reactants. We should end up with a negative value, therefore it's exothermic. Remember, activation energy is from where you start to the top. And now this is for the forward reaction, going from left to right. Going the opposite way, the reverse reaction is right to left. That's what we call the endothermic reaction. So here, this endothermic reaction is in the forward direction for this example. So you start out low, go all the way up, gain some activation energy to the activated complex, and then you drop off to the product side. And here you still end up with a lot more energy than what you started with. So the delta H value is positive. In the reverse reaction, you start off with a small hill and go all the way down here, so it's exothermic in the reverse direction. So the main thing here is to know and compare the products versus the reactants. If your products are higher than your reactants, it's endothermic. If your products are down here compared to your reactants, then it's exothermic, like in the previous example. Now, in order for reactions to occur, we need to have effective collisions. That's according to the collision theory. So when these particles, reacting particles, are jumbling up and they collide with each other, that's how the chemical reaction starts to get going. So we need to have a lot of collisions. So a lot of collisions leads to faster reaction rate. As you can see here, if you have a low concentration, very few particles, you lead to few collisions, whereas if you have a lot of particles, then you have more collisions. Now this slide is going to focus on the factors of reaction rates. So if you want to increase or decrease reaction rates, then you got to use any one of these four. And let's start with the concentration. We saw it on the previous slide. So if you increase concentration, you also increase collisions, as well as the reaction rate. Temperature. Now temperature is a measure of kinetic energy. If you have high temperature, it's really hot. So that leads to a lot of movement and from the particles, they're going to be moving around a lot. And as you can imagine, there's going to be more collisions. The hotter it gets, the more movement, the more collisions. Therefore, the faster rate. Pressure here, if you press down, giving so little room and space for these particles, they're going to have a lot more collisions than before. If you give them little room and increase the pressure by pressing down on them, then you're forcing more collisions and therefore giving a higher reaction rate. Now the catalyst, if you add it, so adding one leads to faster rate for both forward and backward reverse reactions. So the forward reaction goes up, as does the reverse reaction at equal rates. So they both go up. And the way you can see that on a potential energy diagram is right here. I'm going to draw it. So let's say we have an exothermic reaction. What does the catalyst do? It lowers that activation energy and increases the rate for both forward and backwards. So going in the forward direction, we only have to go over a smaller hump than before. And in the same thing in the reverse direction. Before we had to go up this big hill, now we could go over a smaller hill for a faster reverse rate. Okay, now we arrived at the tricky part, equilibrium. It's a state of balance between opposing reactions, both forward and backwards reaction, taking place at the same time at the same rate. Now equilibrium, you probably heard it in bio, and you're definitely going to hear it again next year in physics. It's everywhere in science. Okay, so forward and reverse reaction rates are equal. That's big. The reaction rates are equal. What about the concentration? No. Both sides, all the substances on both sides of the equation do not have to be equal. They just have to be constant. The concentrations have to be constant, reaction rates have to be equal. That's what you need to remember. Okay, now there are 4 ways to stress the system in which you could change the system in a way to disrupt equilibrium. And they are concentration, temperature, pressure, and adding a catalyst. How do they affect the system? Okay. When it comes to each of them, concentration, you're basically changing the amount of substances in there. Amount of substances. And for temperature, I need you guys to focus on heat. Focus on the energy / heat in the equation. For pressure, what you're going to need to do is, focus is only for gases. You're going to have to count the number of moles of gases to determine high and low pressure sides. And the catalyst here leads to no shift. So a lot of things remain the same. The only change here is the reaction rates. It only increases reaction rates for both forward and reverse reactions equally. So there's no favored side, no favored shift. Now, the way I taught my class, in order to help determine reaction shifts, you want to look at the stress and shift the reaction to undo the stress. That's what going back to equilibrium means. And so when you add something, when you put something there, adding it or increasing it, you want to move away from it to get rid of it. So you move to the other side of what you added or increased, whether it's pressure, concentration, or temperature or heat. Now, if you remove something, you took it away, you decreased it, then you want to move towards it so you could put it back. So when you want to move away to get rid of it, and then you want to move towards it to put it back. So that's the usual system response. It wants to undo the stress, so you got to go the opposite direction or towards the same direction in order to put it back or get rid of it. And the final topic is basically entropy. Entropy delta S. Before we learned enthalpy, which is delta H. Let me write a note here. Enthalpy is delta H. Here we have entropy, that's delta S. I don't know what the S stands for, to be honest. And it's a measure of randomness or disorder in the system. And there are a variety of factors to entropy. And let's focus on the states of matter. Gas, liquid, and then solid. Going here from solid to gas, you're increasing entropy. Because from a solid, solids are the most structured, most orderly substance. And so if you're going to the gas, you're breaking those bonds, you increase the randomness and reducing the structure. So you're increasing entropy. Whereas going from gas to solid, you're increasing in order, therefore your entropy is decreasing. temperature now is the same thing. If temperature goes up, so does entropy. The hotter it is, the more randomness will occur. So if particles get hot, they move around a lot. Same thing with pressure. High pressure leads to higher entropy. And lastly, we have to talk about spontaneous reactions. And this here is related to both entropy and enthalpy, or energy. You might see energy as a substitute for enthalpy, or heat of reaction. So the system or the universe tends to lean towards one way for more favorable spontaneous reactions. And so that, in order for that to occur, you need to have high entropy. So that's a lot of randomness. Randomness and disorder. Isn't that interesting? The universe favors randomness and disorder in particles. And low enthalpy. So that's exothermic reactions. So this is a negative delta H. So you want low enthalpy, a negative delta H, which is an exothermic reaction, along with high entropy, a positive delta S, which is randomness and disorder. And I guess that is the end of our video. You should also stay tuned for the practice exam video in which I go through the 27 questions on that practice exam. See you guys later.